Dear students, in this section we are going to learn one very important concept of center of mass, that is velocity and acceleration of center of mass. We will learn the application of this concept through certain illustrations. So let us move to illustration number 1. In this illustration it is given two balls A and B of equal masses are projected upward simultaneously, one from the ground with speed 50 meter per second, that is in the upward direction. You follow the diagram. And second from the top of building of height 40 meter, and it is also projected in the upward direction with speed 30 meter per second. Okay. Find the maximum height attained by their center of mass. That means the center of mass of A and B, we need to calculate what height it will attain. That's the maximum height reached by the center of mass of A and B system. Okay, so let us move to problem analysis part. This is the diagram. Okay, now let us select A and B as a system, ball A and B as a system when they are traveling. When they are traveling, the only force acting on the system, that is the gravitation force, that is the gravity force. That means the acceleration of the center of mass should be g downward direction. Okay, so let us do one thing. Let us find the initial height of the center of mass at the time of just before throwing the balls. So here we write the initial height of the center of mass as y initial c, we can write that is equal to mass m multiplied by 0. Let us take this as the initial level. So m multiplied by 0 for this, plus m multiplied by 40, because this height is 40 meter, and divided by total mass, that is m plus m, that is equal to 2m, and this is equal to 20 meter. This is the initial height of the center of mass just before throwing, or you can say just at the time of throwing. Now let us find the initial velocity of center of mass. Initial velocity of this ball is 50 meter per second in the upward direction, and this is 30 meter per second also in the upward direction. Let us consider upward direction as positive, so we can write UCM equal to m multiplied by 50 plus m multiplied by 30 divided by m plus m. This will be the initial velocity of the center of mass. Okay, now we know, as we discussed, the acceleration of center of mass is g downward direction, and we have taken upward direction as positive. That means the y downward direction should be negative sign, with the negative sign. So acceleration of the center of mass should be equal to minus g. So this is the acceleration of the center of mass. Now we know, for the constant acceleration case, we can apply kinematics equation, right? So here we can apply the equation v square equal to u square plus twice as, because we are required to find the maximum height reached by the center of mass. We know the initial velocity of the center of mass, that is UCM. We know at the maximum height center of mass velocity should be 0. So we should use the kinematics equation, that is VCM square equal to UCM square plus twice ACM h. Okay, h here is the maximum height reached by the center of mass of the two balls. So let us substitute the value. VCM should be 0 and UCM equal to 4. This is UCM. If we calculate, this is value we can calculate here. This is 50 plus 30, 80 divided by 2, m and m will get cancelled. So this is 40 meter per second. Okay, so let us substitute the value in this formula. So this capital H value will be 1600 divided by 20, that is 80 meter. And we know the initial height of the center of mass, that is 20 meter. So we can write the maximum height reached by the center of mass as initial height plus capital H. So this is equal to 20 plus 80, that is equal to 100 meter. So maximum height reached by the center of mass should be equal to 100 meter. In this illustration, it is given a light rope supporting 4 monkeys. You can follow the diagram. These are the 4 monkey 1 15 kg, monkey 2 25 kg, monkey 3 20 kg, monkey 4 40 kg, and the accelerations of the monkeys are given. Monkey 1 upward direction 1 meter per second square, and monkey 2 downward direction and 3 meter per second square, and this monkey is at rest, okay, and this monkey is moving in downward direction with constant velocity, okay. And here we need to find the force of sealing on the rope. This is the question, okay. So let us do one thing. Let us make the diagram to the next page. Let us select these 4 monkey as a system, and if we select these 4 monkey as a system, so this is our system, and in this system we can observe we have one gravitation force, capital Mg. Capital Mg is the total mass of the monkeys multiplied by g, and one more external force acting on the system, that is a tension force, that will be the upward direction. These are the external force acting on the system, okay. And now we know second law, Newton's second law, is applicable for system of the particle. So here we can write F external equal to capital M multiplication ACM. Let us consider ACM is in downward direction. So let us write equation for the center of mass, second law for the center of mass, right? Now let us find the ACM value. Capital M is the mass of the 4 monkeys. So ACM we can write M1A1 plus M2A2 plus M3A3 plus M4A4 divided by M1 plus M2 plus M3 plus M4, okay. Now this monkey, first monkey 15 kg and 1 meter per second square upward. Let us consider upward direction is positive, okay. And this second monkey 25 kg and 3 meter per second square downward. So this is -3. This monkey is at rest. So this A3 equal to 0. And this monkey is also traveling downward direction with a constant velocity. That means this acceleration is also equal to 0. So let us add the masses and substitute the value of the acceleration like this. If we solve this, and this will be 0, and this is 15, and this is 75 negative, and this is 15 plus 25 40 40 80 and 100. So this is the final expression. 0 and 0 will get cancelled. So this is 6 by 10 or 3 divided by 5 we can write, but in the downward direction. Now we can apply Newton's second law for the system of the particle. We can write F net equal to mass multiplied by acceleration. Again we are using, and net force, because acceleration of the center of mass in the downward direction. So here we can write net force, that is capital Mg minus T equal to M multiplied by A. A is the acceleration of the center of mass, okay. Now we can substitute capital M equal to 100, okay, and T we need to find. Capital M is again 100, and ACM we have calculated, that is equal to 0.6. So let us calculate the value of T. T is equal to 1000 minus this is 60. So it is 940 Newton. This is the tension force, and this tension force is also force applied by the support on the rope, okay. In this illustration we are given a uniform rod of mass M, length L. You can observe here this is a uniform rod, that is mass is uniformly distributed over the length, and it is having mass M, length L. It is tied to the vertical shaft. This is the vertical shaft, and it can rotate in the horizontal plane about this vertical axis with angular velocity omega, okay. How much horizontal force does the shaft exert on the rod? we need to calculate the force exerted by shaft, this vertical shaft on the rod. Okay, here we are considering gravity free space. That's why this rod is rotating in the horizontal plane, okay, without inclination. So we are considering the space is gravity free space. So let us do one thing. Let us make the diagram to the next page, this one. Our requirement is to calculate force exerted by shaft on the rod. So for making free body diagram, we need to isolate shaft and rod. That's why we are going to select rod as a system, this rod as a system. Now let us find what are the external forces acting on the system. As we have considered this as a gravity free space, that's why we need to bother about the weight of the rod. The external force only will be the force exerted by shaft on the rod. Now question arises, in which direction this force should be, in the leftward direction or rightward direction. Okay, as we know, this center of mass is rotating about the shaft. That means it should have net force in this situation of the diagram in the leftward direction. That means centripetal force should be toward the leftward direction. That means in this situation given in the figure, the net force applied by shaft on the rod should also be in the leftward direction. Let us make the diagram of this force, this one. Let us consider this force is capital T. Okay, that's why we have made this capital T. Now center of mass of the rod will be at a distance L by 2 from the center of rotation. So centripetal force acting at this position should be equal to omega square L by 2. This will be omega square L by 2. Okay, now we can apply Newton's second law, or you can say equation of circular motion for this case. For the center of mass, we write F external equal to mass multiplied by ACM. This one, right? F external, it is nothing but capital T in the leftward direction. Acceleration, as we discussed, it is again the leftward direction. So here we can write capital T equal to m multiplied by omega square L by 2. This is the force exerted by shaft on the rod. Okay, this is the horizontal force, this one, 1 by 2 m omega square L. In this illustration, we are given a triangular wedge of mass capital M is kept on a spring balance. In the diagram, you can observe this is the spring balance, this is the triangular wedge. A small block of mass small m. This is the small block. That means the size of this block is very small in comparison to this capital M. That is the wedge. And it can move along the frictionless incline on the wedge. In this direction, it can move, and capital M is not moving. It is kept on this weighing balance. What is the reading of the balance while block slide? Ignore recoil of the wedge. That means we need to consider this wedge is fixed wedge. This wedge can be fixed by applying the external force or by the friction between the weighing machine and base of the wedge. Okay, and here we need to find the reading of the balance, reading of this balance. Reading of this balance should be equal to the normal reaction between capital M and weighing balance. This is the scenario. So let us make this diagram to the next page. And first of all, in the case of the center of mass problem, we need to consider our system. So system selection is very important in the center of mass. So let us select our system, as we are required to find the normal reaction, vertical direction normal reaction between capital and weighing machine. So let us select this small m and capital M together as a system. This is our system. Okay, because we are required to find the normal reaction of the base. This is system, and let us assign our x-axis and y-axis. Okay, now in this system, what is happening? Capital M is at rest. That means capital M is not having any acceleration in the horizontal direction as well as in the vertical direction. But small m is sliding along this inclined surface. Okay. And now observe the external forces acting on the system. External forces are the gravity force. In gravity force, we include the weight of this wedge and weight of this block, that is small m, capital M plus small m multiplied by g. This one, these are the weight of capital M and small m. And second force, external force, is the normal reaction applied by weighing machine on the wedge. The normal reaction will be in the upward direction, and one more force is also acting on this wedge, that is the friction imparted by weighing machine on the wedge. Say this is Ny and this is Nx. Nx is the friction, or you can say any external force acting on the wedge. So these are the two forces acting on the base, and this force is acting at the center of mass of the system. So these are the external forces. Okay. So let us find the acceleration of this small m, because acceleration of capital M, as we discussed, is 0. Then acceleration of small m should be equal to along this inclined surface, and it should be equal to g sine theta, right? Let us make the horizontal and vertical component. For the horizontal component, this one, we know this angle is equal to theta. So the component, horizontal component, is the component of this acceleration in rightward direction. So this is equal to g sine theta multiplied by cos theta. Now consider the vertical direction. Vertical direction is the vertical downward direction. So this will be equal to g sine theta multiplied by sine theta, that is equal to g sine square theta. This is the vertical component of acceleration of small m. So we got the acceleration of small m and capital M. Okay. So let us write this acceleration in y direction 0, and this acceleration in the y direction equal to minus g sine square theta, because downward direction we are considering negative. Now let us apply Newton's second law for system. In system we include capital M and small m. So let us apply Newton's second law. We write here, because we are observing here the acceleration of this block in the downward direction, acceleration of this in downward direction 0. That means the center of mass will move in the downward direction, we can say. Okay, but we are not having any guarantee about the motion of the center of mass. So let us consider, let us assume the center of mass is moving in the upward direction. If we consider this center of mass is moving in the upward direction, we can write the equation Ny minus capital M plus small m multiplied by g equal to capital M plus small m multiplied by acceleration of the center of mass in the y direction. Okay, this is ACMY. Now let us calculate the ACMY. ACMY include acceleration of capital M in the y direction plus small m multiplied by acceleration of this block in the y direction divided by total mass. And we have calculated this value equal to 0 and this value equal to minus g sine square theta. So let us substitute these values. Okay, this will be 0. So this is equal to minus mg sine square theta capital M plus small m. As we discussed previously, the acceleration of the system should be in the downward direction. So our assumed equation, that is Ny minus capital M plus small m multiplied by g equal to this one, can be finally written as this minus this, or we can change the sign of this. Okay, so we got the acceleration of center of mass. Now let us substitute the value of the acceleration of center of mass in equation number 1. This is equation number 1. Now we will substitute this value, right? This is minus mg sine square theta divided by capital M plus small m. So let us solving these equation. We'll have Ny equal to capital M plus small m, g plus A cm y. Now substituting this value, this finally give capital M plus a small m multiplied by g minus mg sine square theta. This is the reading of the weighing machine, you can say, or you can say the reading of the spring balance.